Hello and welcome to part 2 of integration methods. In the end, you're going to learn about why we choose certain methods over others when we integrate functions and how they work. Okay, another integration method using partial fractions. Okay, so we have this integral here of 3x plus 11 over x squared minus x minus 6. And you might be tempted to use u substitution to make things look simpler. And specifically, you might substitute this, you might let this be equal to u. But you're going to end up confused because you won't be able to make the substitution and have an integral with respect to du. So let's try and simplify this. Quadratic expressions always look better as factors. So this can be rewritten as 3x plus 11 over x minus 3, x plus 2. Don't forget the dx. Okay. Now what? Well, this method is called partial fractions. We didn't do much here by simplifying, okay? It looks much cleaner, but we didn't really do much here. We can't do u substitution because it won't work. We don't have, so if we let this be u, we don't have its derivative or a multiple of its derivative in the integrand. So we can use partial fractions. How does that work? Well, it basically is a method of rewriting. So we have this 3x plus 11 over x minus 2, x plus 2. How can we rewrite this? Partial fractions, meaning splitting them up. We decompose this whole fraction here. Decompose it into two different functions. X minus 3 plus b over x plus 2. How can we find this a and b here? Well, if we multiply both sides, so let's try and solve this. Let's solve this. 3x plus 11 is equal to, okay, so let's multiply both sides by this bottom expression we have above here. And we would get this is after simplifying. This is what we would get. It's simple simplification. Things will cancel out. If we multiply this by x minus 3, x plus 2, x minus 3 will cancel out, and the same would happen with this expression, but instead the x plus 2 and x plus 2 would cancel out. Now, what are two possible values we have here? We have x is equal to 2, and we have x is equal to 3. And where did I get this from? Well, it's from this expression. And what we could say here is that, okay, we know that this is the numerator, right? This is the numerator, and it's equal to this expression. That means that for each value, x is equal to negative 2, x is equal to 3, they have to be equal. This statement here, this equation has to hold. So let's plug in a value, right? And let's proceed with this. So let's use x is equal to minus 2, negative 2. So we get 3 times negative 2 plus 11 is equal to... Negative 2 here would cancel out because it would be 0. So we'd have b, negative 2 minus 3. This is negative 6 plus 11, 5, which is equal to negative 5b. This is a negative 5, which implies that b is equal to negative 1. And we have our b. I'm going to write it here to the side. b is equal to negative 1. Now let's use our second value. X is equal to 3. So we would have 3 times 3 plus 11. That is 20 is equal to the right hand side now. A times 5 plus, well, 3 minus 3 here in this expression would be just 0. So 0, okay. 20 is equal to 5a, which means a is equal to 4. So we found a. So now we have a is equal to 4. Again, I want to repeat, why did we plug in these values? Well, I got these values from the expression in our denominator after factoring. These are the roots or the zeros of the quadratic. And so we can say that for any x here that we plug in, since this is an equation, for any x that we plug in, these have to be equal. So the numerator here has to be equal to this side for any x. Okay, I'm repeating myself just so it sticks. And we have values already that we can use specific to our problem. X is equal to -2, and another one, x is equal to 3. And now we found specifically what this is. And it is, we have B and A. A we found to be 4. B we found to be -1. So we can write it like this. These two are equal. And we can write our integral as, obviously here what I did is split up the integral. And what we would use to solve these integrals is the u substitution. Why? Because, well, if we let u is equal to x plus 2 here, I'm gonna just explain this part, then we certainly can use u substitution because du is equal to dx. So when we differentiate, we have this function here, and we do have its derivative in the integrand. Its derivative is 1. So we can certainly use this u substitution method. So my main point was just to explain the partial fractions part. So yeah, that's how we use partial fractions to go from a fairly complicated integral to a simpler version.